I'm recording. What's the first question? Read it out loud, please. Ryan?
The first question is, are we doing the pre-lab, or should I mention the pre-lab questions?
Oh, I'm sorry. You know what? Hold on a second. I am thinking about something completely different. So let me log on here for a second. I'm thinking of the old lab that I used to give, and I forgot that I have the pre-lab. Okay, so the pre-lab stuff, no, that's just explaining. So what you're going to do is answer the first 4 questions on that. So what you're going to do is, if you graph this out, what do you get? If you graph that first thing out, what do you get?
You get a graph of the temperature or dew point temperature and the mixing ratio.
Well, not mixing ratio. What are you plotting on the other axis?
Is it the saturation point?
Use the right word, saturation.
Saturation mixing ratio?
Using the saturation mixing ratio, right? And saturation mixing ratio is a measure of capacity. And so what you're doing in this scenario, let me do this. Am I sharing my screen? No. What that would do is this. You're gonna get the same thing that we had before, right? This thing, the temperature versus capacity, and really temperature should be what? Capital. Right? So the key thing here is you're reading that graph with actual values, so that if you're given a temperature, you should know what W sub S is. So in other words, the temperature, when given to you, tells you what W sub S is. In this case, we're meaning the arrows indicates. So I give you a temperature, you give me back from the graph W sub S. However, if I give you the dew point, that gives me back W. So you use the same information for this relationship between the dew point and the actual mixing ratio. So remember, the relative humidity is this over that. It is not the dew point over the temperature. The dew point is what enables you to know what the mixing ratio is, and the temperature is able to tell you what W sub S is. So you use that graph in order to answer those questions. And that's just a really important thing. So does that make sense to all of you here? Temperature tells you capacity, just like the dew point gives W. Now, what is the definition of dew point that we had in the glossary? What is the dew point?
Pressure.
What does it say? Don't all talk at once.
Yeah, you're asking just from like the definition from the notes?
Yeah.
The temperature to which air must cool at a constant pressure in order for dew to form.
Or to reach saturation, right? So dew forming is saturation. What I need you to do is I need you to underline at constant pressure, or highlight it, or whatever you do. Because here's the most important thing. You get to the dew point by dropping the temperature and remaining at constant pressure. You do not lift the air until the temperature drops to the dew point. If air were just sitting around and it was just getting colder, like at night, right? During the night, there's more radiation outgoing than coming in. We've talked about radiation dropping the temperature like that, right? More out than in. Temperature drops to the dew point temperature, and that tells us that we could get saturation. Now, right now, last night, I think we had some light fog in the area. I think the dew point was like 22 degrees, and the temperature was warm during the day. But once the temperature started to drop at night, the temperature dropped to 22 and the air became saturated. So when we go back to this concept here, as the temperature and dew point get closer together, so the temperature keeps going down, which makes this go down. Once they're the same, right? Once the temperature and the dew point are the same, do you agree that W and W sub S are the same? So we drop the temperature at constant pressure to reach saturation. Now, key thing here too is that this difference, right? A minus sign is a difference. It's called the dew point, what?
Depression.
So if the depression is nothing, if these are the same, then the air is obviously relative humidity is saturated, or the relative humidity is 100%. So the greater the dew point depression, the greater or the lower the relative humidity. Does that make sense? Can you write that down? The greater the dew point depression, the lower the relative humidity. How's that sound to you, Aaron? Good? Make sense? So here's the thing that's important to understand. When I lift the air in a parcel, let's say dry adiabatically, what is the temperature going to do? Tim, did you get yourself worked out? Okay, good. What does the temperature do when you lift a box dry adiabatically?
Decreases.
By how much, Aaron?
You know the number? Ten degrees.
10 degrees Celsius per kilometer. I'll finish the units for you, right? 10 degrees Celsius per kilometer. That's the dry adiabatic. Do you understand that the dew point, when I lift air, goes down? What does W do when I lift the air dry adiabatically? What does the mixing ratio do? Zach, you remember?
Doesn't also, well, the W stays the same. but
Right?
the
W
capacity-
stays constant in dry adiabatic ascent. But the dew point goes down by 2 degrees Celsius per kilometer. It's what's known as the dew point lapse rate in dry adiabatic ascent. And that's because the dew point, even though it tells you W, you also need to know what the pressure is. It's set on pressure, because although W, the actual amount of vapor, doesn't matter what the pressure is, the dew point matters what the pressure is. That's why we write at constant pressure. When I lift air, clearly we're not at constant pressure and the dew point drops. So when I go here and I see the dew point going down by, so the dew point lapse rate, and I don't know how you want to write this. Maybe we could do this. Is 2 degrees Celsius per kilometer. And this is in dry adiabatic ascent. The dry adiabatic lapse rate is 10 degrees Celsius per kilometer. That's the temperature. Right? Temperature of the dew point. So if the dew point depression is the difference between them, when I lift a parcel, what's the dew point depression becoming? Hold on. My share. And I'm gonna go to figure that out. And then figure out where the LCL is. Go.
Is it getting smaller?
Always forget to end the recording. Well, I guess I'm not going to end the recording. Okay, we're back. Oh, Kevin, that's what we're doing. Kevin's there. I was like, I didn't even look at the names. Okay, you're back. What'd you get for the answer?
Would it be 8 degrees Celsius per kilometer because the dew point depression is temperature minus the dew point, so it'd be 10 minus 2, which would be 8.
So you're looking at the difference is getting smaller. The temperature is getting smaller by 10, the dew point's by 2. Is that what you got? Tom, you were nodding your head. Is that what you guys said in the other room?
Yeah, more or less.
Okay.
That's the rate it's decreasing at. The depression is getting smaller at.
Okay. And Isaac, how about your room? Did you get that?
We were completely lost.
Okay. What are you lost at, my friend?
I guess we were just having trouble figuring out how to solve this problem. We didn't really know what T was supposed to represent.
Wait, what? T?
Hold on. Did you want us to figure out T minus TD?
This is the dew point depression. It's the difference between the temperature and the dew point. And we know that the temperature gets colder by 10, and the dew point gets colder by 2 degrees Celsius per kilometer, which means that these two numbers are getting closer together by 8. So if I divide by this, I get the LCL height in kilometers. So if I know the temperature and the dew point, and I take the difference, divide by 8, I know how high the base of the clouds would be. So that's how that works. And you have to use it. This is, of course, in Celsius, right? Can't do it in Fahrenheit, but in Celsius, that would be the case. So on a hot summer day, let's say it's 28 degrees Celsius, and the dew point is 20, because it's a temperature. Then, so this, by the way, that's 82 Fahrenheit, and that's 68 Fahrenheit. If I took a box of air and I lifted that box of air, in 1 kilometer, the temperature would become 18, and the dew point drops 2 degrees. So it also becomes 18 degrees Celsius. Since they're the same, we say that the relative humidity is 100%, and the air saturated, that's the LCL.
Okay, that makes sense.
Does that work? Okay. And that's kind of what I'm hoping for. Everybody get that?
Yeah, just really
Could you
quick.
say it again?
What do you want me to say again?
Put that example back up.
Right? Because look, the temperature is decreasing by 10 degrees Celsius per kilometer. The dew point is decreasing by 2 degrees Celsius. So after 1 kilometer of lifting this temperature has dropped to 18. The dew point has dropped to 18 also. Since the temperature and the dew point at the same height is now the same, we know the air is saturated.
Okay.
So that's why if I said, look, you have a box of air that's 28, and the dew point is 20, the air does not saturate when the temperature drops to the dew point. It doesn't get saturated when the temperature drops to 20. Because the dew point is not constant. It is changing also. If this were sitting there on the ground and it just got colder, then the dew point being at 20 is when the air would become saturated and you'd get dew forming or fog or whatever you want to say. But that's at constant pressure. This is when lifting. So this is about the lifting condensation layer. Is that better?
Is that better? Yeah, thanks.
Okay. All right. I still got screen share. Let's go back to the lab. So your job is to do this page of the lab. There should be no reason you can't do more on that. Now let's see what we got. All right, now the rest of this, show me your paper. So put it up to the screen. I want to see what you did.
You said mine.
Yours is on a computer.
Yeah, do you want me to share my screen?
How many did you do, Lena?
I didn't do the example you just explained, but I did all of them except 18 and 19.
Okay, Shannon.
I did the other lab. I didn't do this one yet.
Okay. You saw my message for your notes.
Yeah. Mhm.
Ian, did you do it?
No.
Ryan?
I did like half of them.
Sam?
I'm sorry. I'm getting the. I'm joining the group chat one.
Tom,
I have about the first half.
Zach,
Yeah, I have a few done, like the first half.
Julia, how about you?
I have not started it yet.
Isaac?
I did both of the pre-labs and then I did 2 of these questions as well.
Which two did you get?
The first 2.
Tim?
I got stuck on that first part that we just went over, and then that's about it.
Aaron, how did you do?
She didn't do the page 2, that chart, but we did about 8 of the questions on the 3rd page.
What's the answer to the first one? Don't say it out loud. Fill it in, everybody. And then do the second one.
Like on a sheet.
Zach, you got them both?
Well, no, I'm just like, where do you want us to put the?
Well, you're turning this in before I'll give you a due date in just a little bit.
Oh, okay.
It's number 3. Did you get that one? Who got that one? Lena, you did?
Yeah, do you want me to say what I got?
Not yet.
Okay, I think I got it.
Ryan, did you get that?
For number 3?
Yeah.
No.
Aaron, did you get it?
No.
Anybody else besides Lena? Well, how are you going to get that answer? Lena, send me a private chat.
Okay.
Where are you guys going to get that answer? Yes. What's the instrument called that measures it? Tom, you got the answer yet?
No.
No.
Is my screen being shared? Do you
Yes.
see the chat that I have?
No, not the
No.
chat.
Oh, okay. I was gonna say that'd be bad. Did you figure it out, Lena? Yeah, what's that called?
Ooh,
I see.
okay. Let me see what that's called.
Where are you getting this information, Lena? Share that information with the class.
I forgot where. I'm pretty sure I got just the regular question for number 3 just from the textbook, but I did the. I'll have to find where I found that.
Okay, well, why don't you guys Google that question right now?
I just did. And I think I found the device. Is it called like an atmometer?
A what meter?
An atmometer?
I've never heard of that.
Okay, so it's probably not that then.
What did you Google, Zach?
I looked up the instrument used to measure evaporation.
Well, it doesn't say evaporation. It says evaporative cooling.
Oh, I know.
Oh, okay.
No, don't say it, Sam.
Okay.
You should know it. Tim, what did you get?
Didn't you go over it in that one lecture video we had to watch?
I'm pretty sure.
Yeah, it's. Do you want me to say it?
Yes.
Is it like the wet tip thermometer or whatever?
What's that called? Is that in the notes that I've given you for the class for this unit? What do you have?
The psychrometer?
Take a look here. Right? That's right. That's right. What I just gave you. So it's there, right? And all I'm just trying to do is get you guys to start thinking, how do I find information that's relevant? Well, most of the time, I'm going to give it to you. Every once in a while, I'll say, have I given this? And you're like, I don't know how to find it. And you're looking around and you might be going some weird word that Zach did. But right there, that's the first thing, right? Because if I add heat to water, what does the water do? It evaporates. But what happens when water evaporates? When water evaporates,
Cools.
yes. And what would you say though? When water evaporates, there's something you should say.
Becomes water vapor.
No, I mean, okay, here. When water vapor condenses, what do you say?
Latent heat is released.
That's only 1 out of 12. When water vapor condenses,
Latent heat is released.
so if water evaporates,
Latent heat is absorbed.
that's the word. That's the opposite of release. You absorb it, right? So where does the heat come from? The air. So Tim, in the video that I gave you, that you all needed to listen to and take good notes on, what did I say about animals?
About animals?
Yes. Or what do things do because they want to get cool?
What?
And right, we talked what animals did I reference in that discussion?
Dogs.
And
Pigs.
right,
Pigs.
those are the two metaphors that people say. I'm sweating like a dog. I'm sweating like a pig. And what do dogs and pigs not do?
Sweat.
No, that's ridiculous. If you're sweating like I'm sweating like a dog, I don't have any water on me at all. That's kind of what I'm doing right now. Now, when you sweat, what happens? By the way, when you sweat, did you know that you are giving off pure water? It only stinks because of the bacteria on your skin, but you're actually emitting pure water. So if you were clean, you could just lick it up. But what happens when you sweat?
You cool.
And what's going to cause it to cool effectively? What causes the sweat to cool effectively?
Would it just be ambient temperature?
I don't know if is it just the temperature? You ever been hot and the sweat doesn't help?
Like when it evaporates like off your skin, that like cools you down.
Well, okay, the evaporation does cool you down, but what do you know about the air when the evaporation really is effective and when it's not? There's two things you would do, or there's one thing that you would notice, and there's one thing you would do. Okay, play the imagination game. Let's imagine you're really, really, really hot right now. What are you going to do?
Fan yourself.
Do it. Why are you doing this?
It's creating a breeze
And why the breeze?
to accelerate the evaporation.
Kinda. What is this that you're actually creating?
Wind.
Yeah, a little bit of wind. You're increasing it, but you're doing what to the air? What is this doing to the air?
Movement.
Cycling it?
Somebody said it, Shannon. What'd you say?
Movement.
Movement. Another word. Starting with an M. You're mixing the air. You're replacing the air that's warmed by your body. You're mixing it. And in doing so, it's also going to be drier air. So what is this that you're doing? What kind of a heating process is this? What's the term? What's the technical term for this concept of mixing the air?
Like convection or something?
That's what convection is, right? You're fanning yourself as a convection. But there's something else. You ever gone swimming in the desert? Like Arizona or something? You ever gone swimming on a hot, dry day? That water evaporates really fast. The drier the air, the faster it evaporates. The faster it evaporates, the more cooling. What kind of weather do we have here in the middle of the summer? It's not just hot, it's also what?
Humid.
It's also humid, which means what does your body do? Well, it gives off water, and the water, you want it to evaporate to cool you down. But what does the water do? Is it doing a good job evaporating? So what does the water start to do? It starts to drip because your body keeps pumping out water to try to cool it down. So on a hot, humid day, you don't cool very effectively. So what do you have to look out for your health?
I have a question.
Yeah.
You know, like if you watch like an NBA game, they got sweat all over themselves.
Uh-huh.
How come it? Like, is it like? Does it have to do with the condition of the weather inside of the arena?
To some extent, the problem is, if you're sitting on a hot summer day, just sitting there, you're hot because it's hot. You're conductively heating. But these athletes are running around and they're what is that called? What are they creating a high amount of? I mean, we're running around. Why do you sweat when you run?
Work.
Your muscles get hot.
Your muscles get hot. What is that called? What do you call that rate of energy burning? Starts with an M and it's not mixing. That's your metabolism, right? When you're sitting there, are you burning calories when you sit? Yes. You could sit there all day long and not move and you'll still burn calories because you're generating temperature. Your cells are still doing work. But if you start moving around, you're doing work. Work requires energy. Energy comes from what? The molecules, oxygen. So you're metabolizing, you're creating energy. The more that you're running around, the more energy that you're metabolizing. And so you get hotter and hotter. But your body doesn't want to be hot. It's an amazing ability to consistently keep that temperature consistent. So what you do is you start sweating. That's your body's way of controlling your temperature externally. Now, what do you have to do though if you're sweating a lot, like an athlete or a hot, humid day?
Drink a lot of water.
Because what you're going to do is you're going to start to dehydrate. And if you're dehydrating, now you're not going to have the water that's necessary. So you're going to start to overheat. And when you start to overheat, the first thing you get is heat exhaustion. Like you're feeling hot and you get heat exhaustion. And that's usually starting to be dangerous. At some point, what's the really bad thing?
Stroke.
Heat stroke. If you're having a heat stroke, your body temperature, your body cannot cool yourself down. I tell my storm chasers that because, sometimes we're waiting on these hot, humid days for thunderstorms, and people are out throwing a football around, a frisbee, and they're in the sunlight, and they're generating way more heat than they're used to. Plus, because we're in a van for long periods of time, driving a lot, we try not to pee a lot. So we encourage people not to drink a lot of water during the day. So people get dehydrated and their temperature goes up. And the first thing they're going to start doing is get a little bit dizzy. But if you start getting into heat stroke, what's going to happen to you? What is when you start running a high fever, what do you feel
You
like?
start feeling cold.
You start feeling cold. You start shaking, right? Because everything is out of whack. And if that's the case, I take you to the hospital and you're there for 3 days. Because heat stroke without taking care of that will kill you. Without getting somebody cool down and dehydrated or rehydrated, you're going to die.
I've actually had heat stroke.
Seriously, Ian, tell us about that.
It was like football, and it was like just like August heat, and then I was the only one in my position for the practice that day, so they just had me running, and then like by 3/4 of the way through, all of a sudden I noticed I was just freezing when it was like 90 something, and I was like, wait, this is not right. So then I went to my coach. I'm like, I need to go see the trainer. I think I might have heat stroke, and then I got into an ice bath, and that felt so nice.
Wow. Hopefully you got it before you went to the stroke. You got a doctor?
Oh yeah, no, like I kind of picked up on it like as soon as I started feeling cold. I'm like,
wow,
this is not okay.
Well, good thing the trainer's there. See, now that's the kind of thing where really the coaches should know better. Like, okay, now they're insisting on water breaks a lot. And this is not because you're weak, it's because you're going to die. So you've got to replenish that with water. There's a few things that your body needs. Water is one of them. Oxygen, sugar, and what's the fourth thing? There's 4 things that make you stay alive.
Protein.
Well, I mean, protein, but you can do without protein. You're not going to die without protein. Shoot. Oxygen, water, sugar.
Food.
Sleep in general.
Well, like, if you're ever outside, what do you call when you're overheated? Overheated. What's the word for heat? What's the prefix? What's the word? Therm, right? A thermometer is a heat measurer. So we have a hyperthermia. Hyper, too much. What do you have when you get too cold? Hypothermia. Somebody has anybody been hypothermic? It's a pretty scary situation. You start getting, they tell me that you get a case of the umbles when you're hypothermic. So think of words that end in umble, and this is what you become. So give me some words.
Humble.
Huh?
Crumble.
Crumble. That's the ultimate thing. You crumble to the ground. What else?
You mumble.
You mumble, right? Have you ever seen somebody hypothermic? You can't even understand them. They're just, whoa. What else? You ever try to see you lose your dexterity, so you
fumble.
You mumble. A lot of people are like, whoa, grumble. They become humble. You can barely talk to them. It's a scary thought. So when you have somebody who's hypothermic, you need to get them warm, but something else that you do is you give them candy, give them sugar, and that'll help right away.
What happens faster? Hyperthermia or hypothermia?
It depends on a lot of things. It depends on how effectively the heat source is. Like, what's the easiest way to get hypothermia? Where would you die pretty quickly? What kind of environment?
Cold water.
Cold water, right? Water has a huge heat capacity, and you're going to cool off really fast. Really cold air, if it's not windy, you have this little layer. You got hair. You're protecting yourself. So water is going to be the worst. So you put somebody into ice water, they've got just a few minutes before they'll die. The Titanic sunk. That's how most people die. They didn't drown. They They went hypothermic. So they actually froze to death, which is probably a better way than drowning. But they'd be like floating on the rafts or whatever they could, and then their temperature, core temperature, would drop like crazy, and they would just die. They'd lose consciousness. Anyway, joyful talking. So the idea is this, is if we're gonna get evaporation and it's humid out, it's not gonna evaporate very much. And just as a point of your life, you need to drink a lot of water. Maybe have some electrolytes. Like a great drink is not just Gatorade, it's almost a little bit too sweet, but half Gatorade, half water is a really good way. Maybe a half an orange or something. Get some of those electrolytes. Maybe that's the fourth thing, I don't remember. But in any event, you start to come about and you got to keep that temperature down because your body has a very narrow window. So when people are sick, their temperature goes high, their metabolism goes up, they're fighting, their disease systems are in overdrive. And from what I've heard, that stuff with COVID, the people who suffer really badly, it's that their immune system is hyperactive. Their immune system is actually what starts destroying their respiratory system. In fighting the virus, it's too much and then they go crazy. That's why they're always checking your temperature. If you're not running a temperature, you're probably not much of a threat. So anyway, the higher the wet bulb temperature, the more moist it is. Well, there's an easy machine, not a machine, but a thing called a sling cycrometer. I can't see what I'm spelling, so here, this is what a sling cycrometer looks like. And basically what it is, it's a thermometer. It's actually two thermometers. And one of the thermometers is just hanging there, and the other one is wrapped in this little cloth. Maybe this is a better one. It's wrapped in a cloth that you soak in water. So when you spin it around, the thermometer is measuring the temperature, but the drier the air, the faster that water will evaporate and the cooler the thermometer will read. So the lower the wet bulb, the faster the evaporation, and therefore the drier the air. So the closer the temperature is to the wet bulb temperature, the more humid the atmosphere is. Where's that? So in this paper, it gives you a little relationship that the reality is the dew point is always less than the wet bulb, which is less than or equal to the temperature. They're equal when when the air is saturated. Okay? So that's the wet bulb. That's the sling cycrometer. Make sure you know how to spell it correctly. Sling cycrometer. No, thank you. And when we're out storm chasing, I have one of those. I used to, now I have a little handheld one. But I used to stick it out the window and it'd be really easy. From it, I could determine the dew point. And the dew point, as we saw the other day, is super important, which we'll talk about later today. Anyway, that's that. What's the next question on the lab? Oh, well, you know 4. What's number 5? You should know that one. Give me the answer.
Saturated.
And no, number 5. Number 6 is saturated. Number 5.
Oh yeah, I was looking at 6. My bad.
That's okay.
Point.
Dew point.
Dew point, right? Constant pressure. What's number 7?
LCL level.
Right, it's going to be LCL. What does LCL stand for?
Instant condensation.
Thank you, Shannon. Number 8.
Temperature.
That's what I said the other day, right? Temperature, dry air. Okay, number 10. So what you need to do is you need to kind of look at it this way and say, I've got a mountain. And if I think of the air coming toward the mountain, the air is being forced aloft. Do you understand? This is what we call is lift. Lift is an external source the air's got nothing to do but go up. Now you could say it tries to go around the mountain. And it's actually not as, it's a little bit more complicated than this, but mountains often cause lift. Well, when air goes up a mountain, if I think of it as just a series of boxes, it's going to cool what? At what rate will it cool?
Dry adiabatically.
And if it's dry air, the air will go up and over the mountain and come back down. Okay, now what if sometime during this ascent, a cloud starts to form? Now how will it cool?
It would be the wet adiabatic.
And how much is the wet adiabatic lapse rate? Leanne, how much is the wet adiabatic lapse rate? Like, what's the answer? Aaron, what do you say?
6.
No, remember not say that. Don't ever say that. What's the wet adiabatic lapse rate? That's not the answer I'm ever going to want you to say.
It's the dry adiabatic lapse rate minus latent heat.
Okay, you could say that. If I said, what's the value of it? You'd say it's less than 10. Right? It's less than 10. So Aaron, don't say 6. Or if you say 6, I'm going to fail Lena. I don't want to punish Aaron for saying the wrong answer. I'll punish you, Lena.
What?
Well, I'm trying to resize my window here. There we go. All right. Hey, Aaron, did you guys do the other worksheet?
The other lab, you mean?
Yeah.
Part of it.
Okay. Did you know you had to fill out something? You know what value I had you use for the wet adiabatic lapse rate on the other lab?
I don't
6.
recall. Did you use 6?
I use 6. So if I give on that other lab, if you have to have a number to calculate, use 6. In severe and unusual, Lena, Sam, we use a different one. We use the chart. Here we're going to use 6, but you have to understand it's not 6. It's just something less than 10. So if you have to use a number, you're going to use 6. But other than that, the answer is, what's the wet adiabatic lapse rate? The answer is always less than the dry adiabatic lapse rate, based on the amount of latent heat that's being released. Imperfect present tense. Okay. What about number 11? So I want you to put in the answer, and then I want you to, on the count of 3, I want everyone to respond with that answer. So give me a thumbs up when you have something written in that hole. Okay, if you've got it, go ahead and put your thumb down. I've seen it. How about the rest of you guys? Do you have, do you have an answer, Ryan? You know what's really awful?
Maybe.
It's having.
I don't think I'm right, but.
Well, it doesn't matter, just as long as you have an answer. I hate having a cough because now I think everyone thinks I have COVID. I can't even cough in public anymore. I just got a COVID test back and I'm negative. So you guys don't have to. I'm not going to wear a mask with you on my Zoom meeting, so you don't have to back away from the screen.
Yeah, I got one of these.
Everybody got their answer? Well, there you go. Oh, I feel so much safer now. On the count of 3, give me the answer. 1, 2, 3.
Humid.
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 What did you say, Isaac?
I said dry.
Well, if the drier the air, won't the LCL be higher? If it starts out
yeah.
higher,
Mhm.
then I'd have to lift it further until it became saturated.
Yeah.
So this is kind of what reminded me of your question the other day, is did anybody put saturated?
I did.
Nina did? See, that's what Isaac, we were talking about the other day. It can't be more saturated. The fact that I have a comparative term like more, it can't be saturated. Saturated either is or not. So it has to be something. And the answer is more humid. When I lift the air, it will be, and the LCL will become lower if it's more humid. Right? And then if it's more humid, what does the dew point depression become? Give me,
Greater.
the more humid it is, what's the dew point depression?
Smaller.
Tom's saying lower. Did somebody say greater?
Greater. Mhm.
Greater.
They're inverse, so it has to be. Well,
It's got to be lower. I don't know how to get this into your head because I don't know where the sticking point is if you're getting this wrong. My expectation is, like everything else, you don't own the material when you're studying it. You listen to it and it becomes something that sits on your head. It doesn't actually get into it. We talked about this in terms of the theater and the chairs. The dew point depression is the difference between the two. The smaller that is, I don't have to cool it as much to reach saturation, which means it must be more humid. Yes or no? I mean, Isaac, I'm looking at you and sometimes your face is the only thing I'm gearing my thoughts on because you don't look like you, sometimes you're like, oh, I get it. You didn't look like you were happy. So you're, by the way, I'm gonna go crazy here because remember I told you grammar matters to me. I love my grammar. She's such a nice lady. I said I'm gonna give you my biggest pet peeve in life. Biggest pet peeve word. So I said, look at Isaac's face, and he was like looking at this. And when he's looking like this, right, I knew that he wasn't getting it because usually people get something like, oh, I get it. Mm-hmm. But he was like trying to figure it out. What does he have on his face? He has a look of what? You know what the word is? Whoops. When he's looking like this, what does he look like he's doing?
Confused.
No, confused is different. He's serious thinking about it.
Construed.
Concentrated.
He has
Concerned. Concentrated.
not concentrated. He's concentrated. Concertation. He has a look of, he's concert. God, sorry, not concertation. Conster. What's the letter? Nation. Hold on. I don't even know the freaking way to write this now. Consternation. He has a look of consternation. Have you ever used that term? Do you guys know that word?
No.
Anybody has ever heard that word? Do me a favor, go define consternation.
With my face.
With Google or whatever.
Feelings of anxiety or dismay, typically at something unexpected.
Okay, feelings of anxiety. Would you agree? He's like, oh, he's got consternation on his face. Okay, the thing is, people often say concerned. So what they say is you would say the correct grammar is, I am concerned about something. But people have changed this of the last couple of years, and they go, that's concerning to me. That's concerning. That's not the right word. Everybody uses it. Oh, that's concerning to me. The word is disconcerting or disconcerting. So when like, hey, so I was looking at students and somebody's cheating, and that's disconcerting to me. People go, that's concerning to me. And that's not the right word. And everybody in the whole world uses it. And it drives me crazy because it's wrong and it's going to be acceptable now, and I hate it. So look this word up, disconcerted or disconcerting. What does it say for that one?
Causing one to
Causing one to
feel
feel unsettled.
Right, who's talking? What person who said first? Isaac?
Causing one to feel unsettled.
That's disconcerting to me.
Why wouldn't you
I'm
just say,
feeling unsettled. Say what?
why wouldn't you just say unsettling then?
Well, you could. But the word I always use was that's disconcerting. But people don't say disconcerting. They go, that's concerning to me. And that's not right. Concerns me is about me. That's concerning me. That's about me. What is this about? It concerns me. It involves me. So there you go. And if you're smart, you will hear this and it'll drive you crazy. And then you'll get old and crotchety. And then you'll know exactly what your old professor told you a long time ago about being.
We're saying these words so much that they don't even sound like words anymore.
How about spoon? Anyway, so Isaac's face had a look of consternation, which is disconcerting to me. Now look at his face, right? Now he's smiling and he's all happy. It's like, oh, this is kind of fun. And now I'm all happy. So the other day, what I'm saying is that when it says the LCL lowers, meaning I don't have to lift the air as far to reach saturation, which means it must be starting with higher relative humidities. More relative humidity. But if I have more relative humidity, the difference between the temperature and the dew point is smaller. And then the next question says, what is the difference between the temperature and the dew point called? What's the name of that?
Would it be dew point depression?
That's the dew point depression. So that you know the dew point depression makes me happy. But if I look at you and I think that you're depressed, if you're going through depression, that has me concerned, and that's very disconcerting if I see consternation on your face. And that's your grammar lesson for the day. All right, what's next? All right, this is easy. Number 13.
Add vapor.
All right, I can increase W by adding vapor. Give me a better answer. Not that you're wrong. If you had turned that in, I would have had to give it to you because that's true. But what do you call the process of adding vapor?
Evaporation.
So that's the answer I was looking for. Evaporation. So I can increase W by evaporation, which is adding water vapor. Since W is the amount of water vapor, if I add water vapor, I am definitely doing this. But how do you add water vapor? And the answer is evaporation. In order to have evaporation, what do you need to have present?
Liquid and vapor.
You need to have liquid and vapor, because then you can have that process. And what would the relative humidity be if the air were evaporating? I mean, if the water were evaporating. If it were, subjunctive tense, if it were evaporating, what must be true?
The relative humidity is lower than 100%.
Right. The relative humidity must be lower than 100%. And what's the relative humidity in the cloud?
100%.
So if it were raining through a cloud, would the water be evaporating? No.
No.
Once the rain comes out of the cloud, below the cloud, let's say, will the rain start to evaporate? Yes. But what will the rain do if it evaporates? What will the temperature of the air do?
Cool down.
Because evaporation results in
Cooling.
cooling. How much cooling? How cool will the raindrop become? A raindrop's falling through the sky. As it falls through the cloud, the relative humidity is 100%, the raindrop doesn't evaporate. Now it falls below the cloud and it's falling through the sky and it starts to evaporate. That's going to make the raindrop cooler. What temperature will the raindrop become? What do you think, Ian?
I have no clue.
Well, do you agree that evaporation causes cooling?
Yeah.
What measures the effect of evaporative cooling?
That was the dew ratio, wasn't it?
No.
No, yeah, no, it's pressure. I don't know. I didn't write that in. I was going to do that part later by myself.
Tom?
The wet bulb temperature.
That's the wet bulb temperature. Didn't we do number 3 measures the effect of evaporative cooling, the wet bulb temperature. So if a raindrop is falling and cooling because it's evaporating, what temperature will the raindrop be? And the answer is it will be the wet bulb temperature. The temperature of a raindrop is the wet bulb temperature. The drier the air, the lower the wet bulb temperature, the cooler the raindrop. And the air cools to that temperature. Now, what if the wet bulb temperature were below freezing? Sam?
We're below freezing. When it
What do you think, guys?
Would there be no evaporation?
No.
Turn into snow?
Because the raindrop is evaporating, it is cooling. But it's a raindrop. If it's a raindrop that drops below freezing, what will the raindrop do?
Oh, it will freeze.
It'll freeze. Well, what do you call frozen raindrops?
Hail?
No.
Snow?
No, snow is a snowflake.
Sleet.
It's called sleet. Ice pellets. What's the symbol for sleet? You remember?
Was
it's
it the
like
triangle with the dot inside?
It's the triangle with the dot inside of it. Right?
Wait, I have a question.
Yes, sir.
That's just not freezing air then? Or freezing rain?
That's sleet. So if what basically happens, and we haven't done the first part of this, it starts as snow. It starts as snow, and as the snow falls, it eventually forms into raindrops, liquid water. If the air is dry and the wet bulb temperature is below freezing, then that raindrop will start to become the wet bulb temperature. That's the temperature of a raindrop. It will drop below freezing, so the raindrop, this big chunk, this big water drop, becomes ice. And ice is what we call an ice pellet, which is sleet. So what's freezing rain that Tim's asking about? Sam, explain what freezing rain is.
Rain that freezes as it hits the ground.
Okay, so it stays as water all the way to the ground, Then the ground is below freezing, and now the drop, as it's on the ground, freezes. So that coats everything. So freezing rain is the stuff that glazes everything, and that's the really deadly, dangerous thing to drive on, because you can get that black eye. You don't even know it's ice, because it looks like it's just raining. And if you're walking outside, it's a cold rain, but because your body is above freezing, it doesn't freeze on you. You don't get covered in ice, but the roads do, the cars do if they're outside. So that's freezing rain. What's the symbol for freezing rain?
It's like
Something like a squiggly with a dot in it.
Yeah, something like that, right? So that's freezing rain, that's sleet, and this is snow, and that's rain. So when do I expect sleet? Well, I have to have sleet when the temperature of the wet bulb is below freezing, because the wet bulb temperature is the temperature of the raindrop. So can it rain when it's 33 degrees? Yeah, because if the wet bulb's 33, or let's say it's 34 and the wet bulb temperature is 33, the rain falls, it's 33 degrees, it's still above freezing, stays as rain. But if it's dry air coming in, then the wet bulb is below that, and the rain falling through it will cool it by more, and it'll freeze. And you get ice pellets, little ticks, sleeting, falling on the ground. So if you look in the notes, do you see the word sleet in the notes? I think it's in this unit. What does it say in my notes about sleet? You should be able to do Control F, find it.
Yeah, it's in here.
What does it say? Read it.
It says sleet is frozen raindrops. Sleet occurs when there is a layer of air that is above freezing on top of a sub-freezing layer, little chunks o ice.
Okay, so you have to know it as little, it's not little chunks. Oh, this is not Irish. You have to be Southern. It's little chunks of ice.
What's wrong with
Sleet, sleet's little chunks of ice. That's the way you have to explain it. 35 years of teaching. All my students know it's little chunks of ice. Now, what do you think hail is?
Big chunks of ice.
Did you say of? That's so proper. Big chunks of ice.
Big chunks of ice.
Okay, you know what I'm going to do? I'm going to show you a little. You can put your pencil down. You don't have to take notes on this. Are you seeing my screen? I think so.
Isn't there like a weather phenomenon, like when there's a tornado, like, and there's like a cloud that's hailing because of tornado weather, and the hail can get like sucked into the tornado or something? Something I've heard.
Yeah, sort of. I think you'll like this video. I want to give you just I want to give you just a little break. So if you want to stand up and watch this, this is great. But oh, where is it? Maybe this is it.
It's official. In nearly 2
No.
pounds.
Where is it? Pecos, Hank, Hale. Oh, this might be it. This is a funny video.
You've got 3 possible targets, all the very unstable.
No, this is not it.
A is the weakest.
You guys, if you ever watch this video, holy crap. Do I have to show you this video? I have to show you this video.
Hi, we're Misfit.
Because this is just way too cool.
We rescue organic produce and surplus pantry staples.
This is one of my favorite storm chasers.
I remember the radar from that day.
That's cool with the rainbow, isn't it?
Mhm.
Okay, you got to admit that's kind of cool, isn't it?
Yeah.
I really like him. So I want to show you the stuff he's got of hail, just because we're doing the different types of precipitation, so that you understand what I mean by that. And I need to find something here. Just give me a second. Maybe, is it in labs? Maybe it's in labs. No. Is it in assignments? No, where is it? Oh, movies and animations. Here we go. Tornado videos. No, this isn't it either. Where the hell is it? Lena, I think you saw it. Oh, you know what I think it is? Hold on, maybe I'm in the wrong class. You're probably going, what the hell, Paul, are you doing? But then I'm not teaching anything, so you don't care. Great videos of various weather phenomena. That's what I want. So in here, I got hail. Hey, hail tutorial. There we go.
And this device really
How don't we get that document?
Look at, why does it know that it's doing metabolism? I think it, here we go.
Hailstones crash through windows. They shred trees and crops, pummel livestock, break roofs, wreak havoc on cars and everything underneath its wrath.
Can you hear that okay?
Hail can turn a scorching summer ground into a winter wonderland in minutes. Oh, God. Sometimes baseballs just fall from the sky. Other times, strong winds hurl hailstones sideways like bullets. If you're caught away from shelter during a severe hailstorm, you've got a problem. If you're a storm chaser, hail is your nemesis. Oh, man. No hail, please. Yet you proudly wear your hail dents like victory battle scars. Brand new truck, right? Oh, yeah. A hailstone forms as a tiny water droplet journeys up above the freezing level in some of the most beautiful and dramatic thunderstorms. But how does it get so big? And how big can it get? In an environment conducive of a severe hailstorm, this rising air or updraft is often exploding into lowered freezing levels. This is the factory where hail is made. When the droplet freezes, this process releases heat, which keeps the stone's exterior in a sticky liquid phase. As the little stone journeys through the cloud, it captures more and more water on the surface. The inner layer freezes, and the hailstone grows a layer. You can see the different onion-like layers in many of the stones. Hailstones can also grow by colliding and conglomerating with others. One of the reasons they come in such a myriad of funky shapes. Here's a disc-shaped stone with crystal star-like protrusions. Here's one shaped like a bomb. Here's one shaped like Stewie Griffin. These upward winds sustain ice doubles, and the longer they hang around up there, the larger they tend to get. But some intense updrafts blow up over 100 miles per hour. This is where things really start to get freezing. Eventually, the weight of the hailstone overcomes the updraft winds and falls to earth, often appearing as bright white curtains. Isolated thunderstorms with hail downdrafts set the stage for the most vibrant rainbows. Well, that goes down to the brightest rainbow I've ever seen. That is crazy. If the storm matures into a high precipitation monster, the thick hail core often has a breathtaking turquoise glow. And because these storms often occur in the late afternoon through evening when angled yellow sunlight blasts into the hail core, the yellow and blue make green. There's a beautiful green, that turquoise green color. That's why people associate green storm clouds with tornadoes. When photographing hail, you need a size reference that people can relate to, like a coin, a hand, or Barbie's head. The largest hailstone officially measured landed in Vivian, South Dakota, July 23rd, 2010. It was 8 inches across and weighed almost 2 pounds. I want to know what an 8-inch hailstone would look and feel like, so I'm making an artificial one in my freezer right now. It's almost ready to pull out and smash into something. So how do storm chasers deal with these daily bombardments of hail? Often the same powerful updrafts that create giant hail drop tornadoes. These storms are called supercells, and supercells are shy about people filming their dangly bits. So they throw hail at you and your cameras. There is a foul flap on the ground. Oh, man, the hail is hitting you. In fact, these storms do everything they can to deter storm chasers from exposing their dangly bits to the world. I'm snow plowing. You gotta see how high this is on the side of the road. They cover the road in ice so you can't drive fast. Then they cover the roads in wet, slippery leaves so you can't drive fast. If that doesn't work, they drop buckets of hail to reduce the air temperature to the dew point, causing hail fog. Doesn't that sound like fun, chasing tornadoes in the fog? And of course, if that doesn't slow you down, they break your windows. There's this random gusts that come by and hit us every now and then. Most chasers just avoid the hail cores, often revealed on radar with a pink or purple spot. Other chasers would rather sacrifice portions of their precious view with metal guards to block the icy shrapnel as they punch through cores. Good resist, Daniel. And others have the luxury of thick, super heavy-duty glass to shoot through. Me, I yell 4-letter words at it, and then I call a buddy who just replaces my windows for $100 a pop. I just came inside of my car and broke my windshield. Let's see if that big stone in my freezer is ready to smash into something. So this is roughly the size of the largest hailstone ever recorded. Can you imagine this sucker hitting you in the head at over 100 miles per hour? That hardly did a damn thing. Storm chasers need to mount these all over the cars. Hail injures about 24 people per year here in the U.S. The last hail-related death occurred in Texas in 2000 after a man got struck in the head. On April 30th, 1888, devastating hailstorms killed 246 people in India. On average, hail causes almost $1 billion of damage to crops each year in the U.S. And unlike rain and snow, there isn't a single thing useful about it. Hey guys, check out the size of these hailstones. Hey guys, check out this warm Coca-Cola I just found underneath my seat. Okay, so there is one use for hail. Thanks for watching, friends.
Yay. I love Pecos Hank. So in other words, hail is only associated with what?
Supercells.
Well, supercells. I mean, you could probably go a little bit better. You could say thunderstorms. So thunderstorms are what causes hail. Sleet, freezing rain are wintertime events.
I've seen hail happen in squall lines.
Yeah. They happen in thunderstorms, so they're convective by nature. But it's not like in winter. We expect hail when it's warm out. So the idea of this is hail is associated with convection and thunderstorms, and so hail only forms when the air is unstable. So what kind of a cloud is unstable air?
Was it cumulonimbus?
Cumulonimbus, right? So what kind of rain and freezing rain and snow and sleet comes from what kind of a cloud? Primarily. What's the word?
Sure.
Aaron, do you got it?
She says stratus.
What's the prefix before stratus?
Yeah.
And you're right.
Nimbo.
Nimbostratus. There you go. So we're looking at nimbostratus for sleet and freezing rain and that kind of stuff. Okay. You didn't think we were going to talk about stuff like this today, did you? All right. At what rate does air? Oh no. W is what? What did you write for that? I could accept two answers.
Mixing ratio.
You could say mixing ratio, or you could say
the exact amount of water vapor.
oh, that's even better. The exact amount of water vapor. Exact was another word other than exact you could have used.
Precise.
You could use that. Starts with an A.
Actual.
A B.
Absolute.
Absolute. Which, by the way, if you talk about the absolute amount of vapor in the air, right? Something could be absolute truth as opposed to what? What's the opposite of absolute truth?
Relative truth.
Relative truth. So I have mixing ratio is a measure of absolute amount of vapor. There's also something called absolute humidity. But what's the one that we use? Relative humidity. And what's it relative to? The temperature. The relative humidity is relative to temperature. It changes. So that's how we deal with that. And I love the people when they say there's no absolute truth. That's a self-refuting statement. Do you understand that? If I said there's no absolute truth, do you understand I'm wrong?
Yeah.
Because I'm making an absolute statement that there's no absolute truth, which shows me that there is an absolute truth, which shows me that they're wrong. So there, in your face, disconcerting. All right, number 15. At what rate does air cool in a cloud?
Is it wet adiabatically?
And how much is the wet adiabatic lapse rate?
Less than 10.
Thank you, less than 10. And then the next one is, what is the dew point lapse rate?
2 degrees Celsius per kilometer.
Okay, you would probably put 2 degrees Celsius per kilometer. That's only true if it's dry. What if it's in a cloud? What's the dew point lapse rate in a cloud? What do you think?
Nothing.
It has to be, no, it has to be that. Because remember, a cloud, the air is saturated. Once you're in a cloud, the temperature is going to go down by the wet adiabatic lapse rate. The dew point is the temperature that the air has to cool in order to reach saturation. It's already saturated, so you don't have to cool the temperature. The temperature is going down by The wet adiabatic lapse rate. So what is the dew point going down by? The wet adiabatic lapse rate.
Okay.
Because the temperature and the dew point have to be the same once I'm in a cloud. Lots of little logical statements to make through there. Make sense? What are the two sides of a mountain called? I drew the little picture of the mountain, right?
It's windward and leeward, right?
Right. So I don't even know where my cloud is. Well, I can do it this way. Here's air. Here's air going up and over a mountain. If the air is going this way, this is called the windward side. And this is called the leeward side. Windward, leeward. We also have that in the Caribbean. Have you ever heard of the Windward Islands or the Leeward Islands? And I guess if you were British, you wouldn't say leeward, you'd say leeward. But that's British. They speak weird. Now, number 18 is tough. So what I'm saying is this. Imagine that I've got a cloud like this. Okay, and the air is going up the mountain, and then it reaches the LCL, and it comes up the mountain wet adiabatically. Then it gets to the top, and it comes down the mountain, gets out of the cloud, and then it comes down the mountain. So in other words, there are 4 regions. There's going up the mountain, out of the cloud, going up the mountain, in the cloud, going down the mountain, in the cloud, going down the mountain, outside of the cloud. Does that make sense to you? And I'm asking you, how does W sub S, and RH change in those 4 places? Now, because you guys suck and you didn't do this, I'm going to break you up into groups. So let me do this. Pause share. I'm going to pause the record. Let me record and then share. Okay, there we go. Wish I did. All right. So what I'm saying here is that the easiest one to deal with is this guy, because W sub S is a measure of the capacity, saturation, mixing ratio. So one of the things, as I was in and out of the rooms, do you all agree that actually being forced to talk through and use the terms was new to you? And that's what you have to make second nature. You'll learn better, so you have to say it. Because you're not in a study group, other than the breakout rooms, it's bad. I wish you did have a study group. So if you have to talk to your cat or your dog or your parent or whatever, tell somebody. Look in the mirror and talk to yourself. So listen to me do it. I'm going to do it once through. Listen closely. W sub S is a measure of the capacity. It is the saturation mixing ratio. It is a function of temperature. In other words, it depends on the temperature. So as you go up a mountain, whether you're in or out of a cloud, the temperature goes down. W sub S, as Tim pointed out, is directly proportional to temperature. So temperature goes down, W sub S goes down, going up the mountain. Coming down the mountain, W sub S goes up as the temperature goes up. This and temperature are directly proportional and what? What's the other word?
Corresponding.
Well, they're directly proportional, and what's the other word that describes the graph?
They're exponential.
And they're exponentially
Oh,
related. Right? So they're exponentially related, they're directly proportional. Okay, then what we do is we turn to relative humidity, and I heard a couple people talking about this, that the air in the cloud is saturated. So anywhere in the cloud, the relative humidity is 100%. It just is. And before I do that, I want to think about, okay, well, wait a second. What's happening to W? What does W do here outside of a cloud? What do you know? What did you say?
Does W stay constant?
Mhm.
Right? W is constant when I'm not in the cloud. So W is constant when I'm not in the cloud. Okay. We said W sub S decreases. W sub S increases. And then in this case, then, what we're going to say is the relative humidity is W over W sub S. And as W stays constant, W sub S is going down, relative humidity must go up. So we say RH increases. Coming down the mountain, it's just the opposite. When I'm out of the cloud, W sub S is going up, which means relative humidity is going down. Now in a cloud, because W and W sub S are directly proportional, assuming relative humidity is constant. So when the relative humidity is constant, this and this not only are directly proportional, but they're what? When the relative humidity is 100%, W and W sub S are not just directly proportional, they're also what?
Equal.
They're also equal. So if W sub S is going down, W goes down. And if W sub S is going up, so does W. Does that make sense?
Mhm.
I believe you. When I went to each breakout room, you guys were making good comments, so I believe you. At least I believe the ones who were talking. Now, if you weren't talking, I don't necessarily believe you, but does that make sense? I hope so. If not, you're gonna have to read, watch some of these lectures and figure this out. Okay, now, let's take a look at this mountain and be a little bit more precise. And say that the mountain is 4 kilometers. And I'm going to take a box of air starting over here, and I'm going to say that that box of air is 27 degrees Celsius. What's the temperature at 1 kilometer if the air is going up and it's dry?
17 degrees Celsius.
17. 2 kilometers?
Is it still dry?
Mm-hmm. It's dry all the way up. Because you know how I know it's dry? What did I not draw on here?
A cloud.
So as long as there's no cloud, we know it's not saturated. What's the temperature at 3 kilometers?
-3.
Right? Don't say -7. Did anybody think -7?
For a second.
Ian, don't think that way.
I know.
What's the temperature on the top of the mountain?
-13.
-13. Now coming down the mountain, what's the temperature going to do?
Line up with the other side.
It's going to line up with the other side. I like the way you put that. Do you agree that the temperature will go up in the same way that the temperature went down?
Mm-hmm.
And therefore, when I get to the bottom, what will the temperature of the air be at the bottom?
27.
Okay. Easy peasy, no cloud. Whatever's going up, it's the same as coming down. All right, let's try this. Let's put a cloud in here. Oh, it's easier to draw a cloud than erase the mountain. Okay, now what's the temperature going up the mountain? What's the temperature at 1 kilometer?
17.
Still gonna be the same. 17 degrees C. What is it at 2 kilometers?
7.
7.
Still gonna be 7, right? Because Where does the air get saturated? The air gets saturated at here. So that means from 1 to 2 kilometers in that path, it's still dry adiabatic. Okay, now what will the temperature be at 3 kilometers? See, now you need to be given, you're doing a number. So for when I'm using the numbers, what number did I say it's going to use? Aaron, so funny. Aaron said 6 degrees Celsius per kilometer, and I yelled at her saying, no, it's less than 10, and now you're saying it again. So she's like, I told you that from the beginning. What's wrong with you? But again, this is only when there's numbers. For this class only. For Earth Science 1110. Lena, if you were to take this class first and then go to 11 to 15, you would not want to be saying that, because I will never use 6 in that class, but I will use it here. So what's the temperature of the parcel at 1 kilometer now?
It's 1.
Right? 1 degree C. And then what temperature will it be on top of the mountain? Ian!
This time it'll be -5.
Okay, thank you. -5 degrees Celsius. Now, what will the temperature be down here? What do you say? Is it still going to be 27?
No.
So Isaac, what is now watch this, everybody pay attention. What is the air doing from the ground to 2 kilometers going up? It's cooling dry adiabatically. What's it doing from the ground, or from the 2 kilometers up to the ground? It's warming dry adiabatically. Same rate of warming as it is cooling. What's it doing from 2 kilometers to the top?
Cooling, what did he do?
Wet adiabatic. What's it doing from the top to 2 kilometers? Warming wet adiabatically. Do you understand that the rate of cooling, 2 kilometers to dry, 2 kilometers wet, is equal to the rate of warming, 2 kilometers wet, 2 kilometers dry? So that means you should end up at the same temperature on both sides of the mountain. Everybody capiche with that?
Yeah.
All right, so then let's try this. What if the cloud looks like this? Again, it's easier if I draw a cloud than erase. And now the cloud is forming at 1.5 kilometers on the leeward side, and it's evaporating at 3.5 kilometers on the windward side. I'm sorry, the other way around. 1.5 kilometers on the windward, 3.5 kilometers evaporation on the leeward side. First question is, go ahead and everybody take the time to calculate what is the temperature on top of the mountain. So just fill it in. And don't forget, I'm now doing half kilometers. So if it's 10 degrees per kilometer, how much is it per half kilometer? At 5. And same with the wet. Okay, so go ahead and do that. Give me a thumbs up if you have the answer. All right, give me the answer. Go ahead, Isaac. What did you say for the top of the mountain?
-3.
Is that what everybody got?
Yep.
Give me a thumbs up if you got it. You have to give me a thumbs up. Okay. Well, if that's the case, then, I mean, seriously, on a test, is it going to, how hard would this be able to do on a test? Right, so it's going to be 17 here, and then it's going to cool dry adiabatically until 1.5, which would mean it drops by 5, so it's 12. And then it's going to go wet adiabatically to here, which means it's going to go to 9. And then it's going to go down by 6, so it goes to 3. And then it goes up 1 more kilometer, it goes to -3. What's the temperature down here?
35.
So it's -3, then it goes to 0. And then it goes 1/2, so it goes to 5, 15, 25, and 35. Now, the other way that you could look at this, and I think this is important. Remember how we were talking about how is it cool and how it warms is like opposite on both sides of the mountain? In this case, from here to here, it's the same as it is from there to there. Do you agree? And from here to here, it's cooling at the same rate that it's warming. But from 1.5 to 3.5, how is it cooling? At 6 degrees Celsius per kilometer. How is it warming on the other side coming down? 10. It's cooling slower than it warms. If that's the case, for every kilometer different, it should be how much warmer? For every kilometer different, how much warmer should it be?
4 degrees Celsius.
Right? It's the difference of 10 and 6 should be 4 degrees warmer. So how many kilometers different was it? It was 2. So it should be 8 degrees warmer than it was. It was 27 plus 8, 35. A nice little way to check your answers. Now, do you understand how that works? Is this super duper difficult? I mean, we've done a lot of hard things. This is pretty straightforward, isn't it? See, what I like is if you work your brain to get hard things, easy things come easier. Like, oh, this is easy. Now, the question is, why does the cloud look different on both sides of the mountain? So what do you think?
As it was raining.
Because it rained. Oh. Okay. So what I want you to think about is this. I'm going to do this for a second. I'm going to pause the share. I'm going to move you guys back here so I can not look sideways to teach you, tell you a story. I have a little story time, so put your pencil down and just pay attention, okay? So I come from this weird country, and there's only one rule that's kind of different than here. 2 rules. One of them I can speak freely. The other one is that when I walk up a mountain, I can only have a limited amount of money. Sorry, that was I just made a political statement. I feel like my freedom of speech is totally gone in this country. If you only knew what it was like 5 years ago, I feel like I could say anything, and now I'm afraid of everything. So I'm living in another country, so I decided I would give myself free speech. But when I walk up a mountain, they have a limit to how much money I can have. But fortunately, up and down this mountain, there's a whole bunch of ATMs. Okay, so I start out with a certain amount of money, and I've got that money, and I go to the first ATM machine, and eventually it says, okay, you have more money than you can have. You have $50, but you can only have 40. So what do I have to do? I take $10 and I put it into the ATM. Now, do I have any money left? Yes, I have $40. I go up a little bit higher and I go to the next ATM machine. So you have too much money, you have to get rid of some. You have to take some of your assets and make them liquid. Get it? Cloud turning. So anyway, I put it in, it says you can only have $15. Okay, so I put some more money in there. Then I go up a little bit higher, there's another ATM machine, and it says, oh, you have too much, put another $10 worth. So I put another $10 worth. And I go to the top of the mountain. Do I have money? Yes, I've got $5. Now I come down the mountain, and as I come down the mountain, of course I can have more money now. So I go to the first ATM, I take some money back out. I go to the next ATM, I go to the next, take some more money back out. I go to the last ATM, I take all my money back out and go to the bottom of the mountain. How much money do I have at the bottom of the mountain on the other side? Based on the score. I still have $50. I have the same that I started with, right? So I'm like, okay, kind of a weird rule, but whatever, I can live with it. So the next day I decide I'm gonna go walk over the mountain again. And I do the same thing going up. And then I start coming down and I take out some money. And then I get to the next ATM, the second one down. And I go, okay, I want my money back out. And the ATM goes, I don't have any more for you. Now that would make me really angry. I'm screaming. I'm like, what? Where's my money? I've only got $20. I started with 50 and I've only got $20. Where's my money? So notice the anger in my voice. And the ATM machine says, don't worry about it. I'm saving it for you. I'm like, you're saving it for me? What the hell are you saving it for? And what does the ATM machine respond with? I'm saving it for
Rainy day.
a rainy day. Ha, ha. You see, what happened is when I go up the mountain, I'm taking vapor. Julia, she's like, I'm trying not to smile, but it's kind of quick. I'm going up the mountain and I'm taking vapor and I'm making it liquid. And if I have that same amount of liquid in the cloud coming down, it goes back into vapor. But when it's liquid in the cloud, if it starts to rain out, where's the liquid going? Into the ground. It's come out of the air. So when I come back down the mountain, I have less liquid to get back. Okay, so now let me do this. Oh, well, I don't have to stop. So I need to do this. I need to pause recording in a second. So what you're going to do is you're going to do the next question with your group. Okay, because that's talking about the starting on the windward surface, comparing it to the leeward surface of W, W sub S, and RH. Okay, so pause record. Is everybody back? Yes. Is everybody back? No, room 3. Those guys are just slacking. Did you get the right answer, Aaron? You're not sure? All right, let's try. I got the recording going. Oh, I need to share this. Resume share. Okay. And let's go with this guy. So what I'm doing is I'm comparing those 3 terms on from the windward side versus leeward side. So W, W sub S, and RH. And W sub S and RH. Okay, so what's the first one here? What's the relationship between the two? What'd you put, Tim?
For W,
Mm-hmm.
I feel like it wouldn't change between the two.
Well, remember this is,
it would be constant for longer on the leeward side.
well, it's constant, but I mean, where I start, like think about the money. Do I start with more money and end with less, or the other way around? Or do I end up with the same?
You started with more money.
I started with more money. Where did the money go? It rained out. So that means I have more vapor to begin with than I do over here.
Okay, that makes sense now.
You guys got that?
Right.
Okay, well, what about W sub S? What did you say for that? Shannon, what did you say for that one?
Wouldn't W sub S be higher than the leeward side?
Like that? Is that what you're saying?
It might be lower because it rains. So
No. What does it depend upon? What does W sub S depend upon?
temperature.
Right. Where is it warmer?
Okay. Yeah.
It was 35 degrees over there, right? It's warmer. So that means if it's warmer, it has a greater capacity. So that means it's this way.
Mm-hmm.
Does that make sense? Now, what about the relative humidities? Remember, the relative humidity is this over that. So in this case, we don't have simple proportions. W, on the leeward side, W is less, and the capacity is more, which makes the relative humidity what?
Less.
Not just less.
A lot less.
A lot less. So what I would do is I would say, it's a lot less. So when you have air going up a mountain, when you're on the windward side of the mountains, it tends to be much more humid and rainy. On this side, it tends to be much drier and warmer. We call this a rain shadow desert. Does that make sense? Because it's warmer, because it's raining. So you ever been out to the Cascade Mountains in Washington or Oregon? Anybody ever been to those two states? It's really wet. It's not tropical rainforest, it's a deciduous rainforest, but it's rainy. Think about Seattle, it rains all the time because this moist humid air comes up and is forced up and it rains out. But you go over the mountains toward Eugene, Oregon, Spokane, Washington, then you've got really dry areas. And that's because it's a rain shadow desert. Now, what about, does everybody have questions on this before I erase it? Okay, well, what about in Colorado? What about in Colorado? So here's Colorado. Big boxy state with a bunch of mountains in the middle of it. What side's the windward side?
Western side.
Not necessarily. If the winds are blowing this way, generally speaking, then what is this area, the Front Range, going to be like in Colorado?
Mm-hmm.
This would be really dry.
Mm-hmm.
And in the summertime, it really can be. But do the winds always blow from west to east in Colorado? And the answer is no. Sometimes the winds come out of the southeast, where the Gulf of Mexico is bringing moisture. So all of a sudden, this side becomes the windward side. And that's when you get the really big snowstorms into Denver. But then the winds come the other way, it warms up, it gets dry, and what does all the snow do? It melts. There's an old Eskimo word for the type of wind. It's called a Chinook wind. You may have heard Chinook for a helicopter. This is the Chinook wind, Chinook. And you know what the Eskimo word Chinook means? Snow eater. It's because you can get in May, Colorado, the Front Range can get 15 inches of snow. And the next day the winds are like out of the west, temperatures get up to 60 and the snow goes away. What happens when it snows here? Usually behind it gets really cold and not fun. Okay, so that's what we're talking about. Now let's take, you still see the screen? And I guess that's the end of this lab. Okay.
You know, could you, the table on page 2, I'm not sure how to read that.
Okay, what I'm saying is that this is either the temperature or the dew point. If you're saying this is the temperature, if T, then W sub S, then the value here is W sub S. Okay. If you're saying that it's the dew point, then what? Then the value you read from here is W. So for instance, let's say the temperature is 70 degrees Fahrenheit and the dew point is 45 degrees Fahrenheit. Okay, what's W sub S based on the chart? Everybody?
6.4?
No, 70 degrees.
Oh.
15.95. 15.95 what?
Grams over kilograms.
Grams per kilogram, right? Okay, and then if the dew point's 45, what's W?
0.4.
6.4. So the relative humidity is W over W sub S. This is showing my work is 6.4 grams per kilogram divided by 15.95 grams per kilogram. Grams per kilogram units go away. That's why you're a percentage. You take a calculator, you divide it, you put it in a percentage. That's easy. Does that make sense? Where did you go? Where'd they go? Oh, there you are, Aaron. Did somebody just leave? Who left? Who dropped out? Julia. Okay, that's how you do this. So pretty easy, yes? Now, penalty. Listen to me. Because you didn't do your work on this, this is due tonight at midnight. Can everybody get it done by midnight tonight? Is there anybody who has to like leave and go to work or something?
I have to work like right after this.
Till when?
So, 10:30, so I could probably get it done.
I tell you what, I will make it due by, how about 10 a.m. tomorrow?
Yeah.
Thank you.
Okay, I'll do that. So 10 a.m. tomorrow. Now, this, oh, I suppose I should log in. This other lab, instability lab, has got this stuff. We've done information that you should be able to do this. Can you do this? No, you can't. Okay, I expect, and I don't know, what am I going to do to check it? I may give you 5 points or give you 0 points on Tuesday if you don't have this. I need the pre-lab done, and I need this through this page, through 5. Do not worry about this last part. Okay, am I clear? But you have everything you need in this stuff to have it done. So you need to show me. You cannot come, I will boot you out of class if you don't have it done. The stuff that you're turning in by 10 a.m. tomorrow morning, it better be really good. You have all the answers. Make it neat, make it professional, write full sentences. You have everything that you need to do it. Right? You have all the answers. We went through the whole thing. So are we good with that?
I have
Okay.
a quick question.
Yeah, go ahead.
For the instability lab, you said through 5. Do you want us to turn that in or just have it done?
Just have it done.
Okay.
Because when you turn it in, I want everything turned in. I'll make it due next week.
Okay, thank you.
Because I don't think you're just not ready to do that last section yet. We still have lecture to deal with that. Okay, so everybody's good with that? Now, the other thing that's coming due is your lab here. This is called the geography lab. What else is due what else is due by the end of the day Sunday? Like, is there another chapter notes? Probably. Are you there?
Yeah, chapter 15, the reading
Chapter
assignment.
15. Okay, so what I'd like you to do is this geography lab is going to be due sometime next week. Some of you have already kind of done stuff. Aaron, I think you've already done it. Julia, you may have already done it. Did you do it, Shannon? No.
Yeah, I turned it in. Yeah.
Okay, so if you want to improve it, but basically it's just making sure you know your states. Did you find that it was pretty self-explanatory?
Mm-hmm.
Writing on a blank map. So in here, and I think, I'm trying to remember if I changed anything. Yeah, it's just doing this thing. So what I need you to do, it says work in a group of 2 or 3 and answer those questions. You're going to do that independently, unless, I mean, you're welcome to talk to each other about it, but I want you to do this. So you should be able to do the geography lab and get a head start on it. I'm not going to collect it right away because I don't want to make it like oppressive, like, oh my God, I have so much to do for Monday, but it's coming due. So you need to do at least half of it, whatever. And the lab's a lot of points on this one. It's like 50 points, but you need to know your state. So when I talk about the Cascade Range, you would know where I was talking to, and you know where Oregon is and all this other stuff. So, you know, if you're sitting around watching TV and you want to do some stuff, watch some TV and work on the lab, and because it's really more neatness and making it pretty and drawing diagrams. It's pretty simple to go through. It just takes a little bit of time. So I won't make it due by Monday or Tuesday, but it'll be due sometime after that. But start working on it.
Yeah, well, with mine, I just input like the graphs I saw online because I couldn't like draw the map. So they were what you asked for though.
Okay. Okay. 2-letter postal abbreviations, that kind of thing. So that's just, it's sort of a lab thing that you can kind of do on your own time. I think that's fair. Is that good? So this lab that we just finished today, written up super neatly, super professionally, get it done by 10 a.m. tomorrow. Then do most of the lab in chapter 15 for Monday and start working on the geography. So, because that'll be due also at some point. Not next week, but probably the week after will probably be the next test. And it'll be just like this last one. So everybody good? What's your level of understanding from the stuff we did today? What's your feeling on that one? Okay, I've got a couple people with 5s.
Or
I got some 4s, a couple of people flipping on 3s, and that's, you can do better. Isaac, how you doing on that? Aaron, what number are you?
4.
Excellent. Okay, so Ian, Sam, you guys stick around. And the rest of you guys have a wonderful weekend. If you have any questions, let me know. And I'll
You know-
see you next week.
We had a question about the chapter 6.
Oh, okay. Let me do this first.